What if everything you thought you knew about the universe was built on a foundation that isn't as solid as it seems? We grow up learning that the laws of physics are fixed, unchanging truths that govern everything from the smallest particles to the largest galaxies. The speed of light, the pull of gravity, the way atoms bond, these aren't just rules, they're the bedrock of reality itself. But what if that bedrock isn't as permanent as we believe? What if the laws of physics themselves are slowly, subtly evolving over time? This isn't just a wild thought experiment or the plot of a science fiction novel. It's a real, urgent question that physicists around the world are investigating right now. Imagine a universe where the strength of gravity was once stronger, or the fine structure constant, which controls how atoms interact with light, drifted ever so slightly over billions of years. If true, it would mean that the universe doesn't play by one set of rules forever. Instead, it might be more like a living, breathing entity, growing and changing in ways we're only beginning to comprehend. In this video, we're going to explore one of the most profound mysteries in modern science. Are the laws of physics themselves evolving? We'll travel from the insights of ancient philosophers to the bleeding edge of quantum theory and cosmology, hearing from researchers who are measuring the echoes of the early universe for clues. We'll look at startling evidence that suggests some constants may not be so constant after all, and we'll ask what it would mean for us if the rules of reality aren't set in stone. This journey will challenge everything you assume about order, constancy, and the nature of existence itself. So join me as we step inside the mind of the universe and ask, is physics itself alive with change? Long before telescopes and particle accelerators, some of the greatest minds in history were already wrestling with a fundamental question about the cosmos. Does the universe operate by fixed, unchanging rules, or is it subject to the whims of capricious forces? The ancient Greek philosopher Aristotle gazed up at the night sky and saw two distinct realms. Here on Earth, he observed a world of change and decay, a place where things are born, grow old, and die. But the heavens above were something else entirely. To Aristotle, the celestial sphere was a place of perfect, eternal order, where the stars and planets moved in flawless, unchanging circles around the Earth, governed by a divine and permanent mathematics. This idea of a perfect, static cosmos would dominate scientific thought for nearly 2,000 years, but not everyone agreed with this vision of permanence. Other traditions, like those in ancient Hindu cosmology, envisioned a universe caught in an endless cycle of creation, destruction, and rebirth, a concept known as the Kalpa, where entire universes expire and are born anew in vast cosmic breaths. Even the famous mathematician Pythagoras, who saw numbers and geometry as the ultimate reality, believed in a music of the spheres, a harmonious but potentially dynamic order governing the cosmos. This tension between a universe of fixed perfection and one of dynamic cycles set the stage for all future inquiry. Centuries later, when Isaac Newton formulated his laws of motion and universal gravitation, he too operated from a place of deep assumption. He believed he was uncovering eternal, immutable truths that had been set in place by a divine creator, and that applied equally everywhere for all time. His laws became the unshakable foundation of classical physics, a testament to a universe governed by consistent, predictable rules. And yet, even in Newton's work, if you look closely, there are subtle hints of something more. He famously struggled to explain the long-term stability of the solar system, eventually suggesting that God might occasionally need to step in and correct planetary orbits to prevent chaos. This tiny admission reveals a flicker of unease, a quiet question lurking beneath the surface of absolute certainty. Is the cosmic order truly as stable as it appears, or could there be a hidden dynamism at the very heart of reality? This historical context is crucial because it shows us that our modern questioning is not some radical new departure. It is simply the latest chapter in a conversation that has been ongoing for millennia. The key difference is that today, we are no longer limited to pure thought and philosophical debate. We have the tools, the mathematics, the technology, and the observational data to move from speculation into the realm of testable science, to finally ask the universe itself whether its laws are written in stone or in something far more fluid. But then came Albert Einstein, and with him, a revolution in our understanding of space and time itself. His theory of general relativity painted a cosmos far more dynamic than Newton could have imagined. It revealed that space and time are not a static, unchanging stage, but a flexible, interwoven fabric that can warp, bend, and stretch under the influence of matter and energy. This was a universe in motion, a cosmos that could expand or contract. And yet, when Einstein applied his own breathtaking equations to the entire universe, he encountered a problem that challenged the prevailing wisdom of his era. The scientific consensus, deeply influenced by centuries of thought, held that the universe was eternal and unchanging, a steady, stable island of stars. His equations, however, naturally suggested a cosmos that was either expanding or contracting. Unwilling to challenge the idea of a static universe, Einstein made a fateful adjustment. He introduced a fudge factor, a term he called the cosmological constant, a kind of repulsive force that would counterbalance the pull of gravity on the largest scales, effectively propping the universe up into a state of perfect, unchanging equilibrium. It was an elegant mathematical solution, but it was born from an assumption, not from observation. This assumption was shattered just over a decade later when Edwin Hubble, peering through the Great Telescope at Mount Wilson, made an astonishing discovery. The distant galaxies weren't stationary, they were all rushing away from us. The universe was not static at all, it was expanding. Einstein famously called his introduction of the cosmological constant his biggest blunder, not because the concept itself was wrong, but because he had used it to cling to an outdated idea of a stable, unchanging cosmos, blinding himself to the dynamic reality his own theory had predicted. This pivotal moment in history is so much more than a simple anecdote about a genius making a mistake. It is a powerful lesson about the deep-seated human desire for permanence and stability. Even one of the greatest intellects of all time felt the gravitational pull of the assumption that the cosmos must be governed by fixed, eternal rules. His theory of relativity itself is built on the idea that the laws of physics are the same for all observers, a principle known as covariance. But it also tells us that measurements of space and time are relative. They depend on your frame of reference and your motion through the universe. What is simultaneous for one observer might not be for another. This inherent flexibility hints that our experience of reality's rules is not absolute. However, relativity in its classic form still assumes that the underlying laws themselves, the equations written on the cosmic chalkboard, do not change. They are the same here as they are in a distant galaxy, and the same now as they were billions of years ago. Einstein's work, therefore, embodies a profound tension. It gave us a dynamic, evolving stage, the fabric of space-time, while simultaneously insisting that the script for the play, the laws of physics, remains forever unchanged. This tension set the stage for everything that followed. It forced scientists to ask a much deeper, more radical question. If our most fundamental assumptions about the stability of the cosmos can be upended once, could it happen again? If the stage itself can evolve, is it really so unthinkable that the script might be undergoing subtle revisions as well? Einstein's blunder opened a door in the scientific mind, a door that leads from a universe of fixed, eternal laws to one where even the most fundamental constants might have a history of their own. Just as Einstein was redefining the fabric of space and time, a parallel revolution was brewing on the smallest of scales, one that would introduce a universe of profound weirdness and possibility. Quantum mechanics shattered the classical clockwork universe, replacing certainty with probability and solid matter with shimmering waves of potential. In this bizarre and counterintuitive realm, particles can be in two places at once, communicate instantaneously over vast distances through entanglement, and pop in and out of existence from the void itself. But amidst this seemingly chaotic dance, there are anchors, fixed points that bring order to the quantum fog. These are the fundamental constants. Think of them not as mere numbers, but as the fundamental settings on the control panel of reality. Planck's constant, for example, dictates the size of the quantum world itself. It's the reason energy comes in tiny, indivisible packets called quanta. Without it, the stability of atoms would vanish, electrons would spiral into the nucleus, and all matter would collapse in a catastrophic instant. Then there's the fine structure constant, often denoted by the Greek letter alpha. This number, approximately 1/137th, is arguably even more mysterious. It governs the strength of the electromagnetic force, which is responsible for holding atoms together, for the chemical bonds that create molecules, and for the very light we see by. It is a pure, dimensionless number, a ratio of other fundamental constants, and it appears to be exquisitely fine-tuned. If alpha were even slightly different, the universe would be unrecognizable. A fraction larger, and stars would burn through their fuel too quickly for life to emerge. A fraction smaller, and complex molecules necessary for biology might never form. For a long time, these constants were simply accepted as the immutable, non-negotiable rules of the game. They were the fixed parameters plugged into the equations, the bedrock upon which all of quantum physics was built. The sheer success of the theory, accurately predicting everything from the behavior of semiconductors to the inner workings of DNA, seemed to confirm their permanence. But then, a brilliant and daring mind began to ask a heretical question. In the 1930s, physicist Paul Dirac, one of the founding fathers of quantum mechanics, was struck by a strange numerical coincidence. He noticed that the ratio of the electromagnetic force to the gravitational force between an electron and a proton is a staggeringly large number, around 10 to the 39th power. Even more curiously, the age of the universe expressed in certain fundamental units is also a number of a similar, mind-boggling magnitude. To Dirac, this couldn't just be a random accident. He proposed that these enormous numbers might be connected, and that the only way for that connection to hold over the vast expanse of cosmic history would be if the so-called constants weren't constant at all. He suggested that the strength of gravity might be weakening very slowly over billions of years. This was a radical idea, that the very forces of nature could be evolving, that the control panel settings of the universe might have dials that turn, however slowly. Dirac's specific hypothesis may not have held up to later scrutiny, but the seed he planted was profound. He opened a door in theoretical physics, showing that quantum theory itself does not necessarily forbid the evolution of its own foundational numbers. The equations of quantum mechanics are incredibly powerful, but they don't explicitly demand that alpha or Planck's constant must be frozen in time for all eternity. This theoretical possibility transforms these constants from static numbers into potential characters in the cosmic story, values that could have a history and a future. This opens up a breathtaking new way to solve some of the deepest puzzles in modern cosmology. Could a slight drift in the strength of electromagnetism explain why we see certain anomalies in the light from the most distant quasars? Might a slowly changing gravitational constant resolve the troubling discrepancies in how we measure the universe's expansion rate? The idea that constants could drift offers a potential escape hatch from some of the most stubborn dead ends in physics, suggesting that our universe isn't built on a rigid, unchanging foundation, but on a more fluid and dynamic order, a cosmos that is not just expanding, but maturing and evolving in its most fundamental nature. So if the constants aren't necessarily set in stone, where do we even begin to look for evidence of their change? The search leads us to one of the most precise numbers in all of physics, a value so crucial it's known simply as the fine structure constant, or alpha. This isn't some obscure, complex formula. It's a pure number, approximately 1 divided by 137, and it controls the very strength of the electromagnetic force. This is the force that dictates how tightly electrons bind to an atom's nucleus, how atoms link together to form molecules, and even the specific colors of light that every element absorbs and emits. For decades, this number was considered a fixed pillar of reality, an unchanging rule written into the fabric of the cosmos. But then, astronomers began to look back in time, and the pillar seemed to show a tiny, almost imperceptible crack. The key to this detective work lies in the most powerful time machines we have, giant telescopes pointed at incredibly bright, distant objects called quasars. These are the blazing cores of ancient galaxies shining across billions of light years. As their light journeys through the vast emptiness of space, it passes through enormous clouds of primordial gas. Atoms within these clouds are picky eaters. They absorb very specific wavelengths of this background light, leaving behind a unique fingerprint of dark lines in the quasar's spectrum, like a barcode imprinted by the universe itself. This barcode is dictated by the fine structure constant. If alpha has always been the same value, then these absorption lines should appear in the exact same patterns we observe in laboratories on Earth today, just shifted to redder wavelengths due to the expansion of the universe. But that's not what some teams started to find. Using incredibly sensitive instruments on telescopes like the Very Large Telescope in Chile, scientists led by researchers like John Webb began to analyze these ancient barcodes. They reported something astonishing. In the light from quasars so distant their light has been traveling for over 12 billion years, the absorption lines were slightly off. The patterns suggested that long ago, in those far-reaching regions of space, the fine structure constant was minutely smaller, by about 1 part in a few 100,000. It's a change so small it seems almost trivial, but in the hyper-precise world of fundamental physics, it's a potential earthquake. A different alpha in the past would mean the force of electromagnetism itself was weaker, which would have cascading effects on how atoms behaved, how stars fused their elements, and ultimately on the entire history of the cosmos. Unsurprisingly, a claim this monumental has been met with intense scrutiny and fierce debate. The entire endeavor is a breathtaking feat of precision measurement, pushing our technology to its absolute limits. Critics rightly point out the immense potential for hidden systematic errors. Could the observed shifts be caused by unknown contaminants in the interstellar gas clouds themselves? Perhaps different isotopes of elements were more common in the early universe, subtly altering the absorption pattern without any change to the fundamental constants. Maybe the issue lies with the telescopes and instruments. After all, calibrating equipment to such an extraordinary degree of accuracy over such vast distances is a Herculean task. Every variable must be accounted for, from the temperature of the detector to the subtle movements of the Earth's atmosphere. Proponents of the varying constant hypothesis have worked tirelessly to rule out these other explanations, analyzing data from multiple telescopes in both the northern and southern hemispheres to cross-check their results. The controversy continues, with some independent studies supporting the finding and others finding no evidence of change at all. This healthy, rigorous debate is science at its best, a relentless pursuit of truth where extraordinary claims must survive an onslaught of skeptical inquiry. Whether the final verdict confirms a drifting constant or not, the very fact that we can have this debate, that we can measure the universe with such exquisite precision to ask the question, is a testament to how far we've come. We are no longer just philosophers wondering about the cosmos. We are detectives, holding a magnifying glass to the light of creation itself, searching for clues that the rules of the game might have been written in slightly different ink long ago. While the fine structure constant governs the electromagnetic force, there is another, equally fundamental number that physicists are scrutinizing for signs of change. This is the proton-to-electron mass ratio, often represented by the Greek letter mu. It's a remarkably simple concept. It's just the mass of a proton divided by the mass of an electron. That number is approximately 1,836, meaning a proton is nearly 2,000 times heavier than the tiny electron orbiting it. This ratio is absolutely critical because it acts as a master setting for the world of molecules and chemistry. It determines how atoms vibrate against each other, the precise energies required for chemical reactions, and the unique spectral signatures that every molecule emits its own specific light fingerprint. To search for any drift in this cosmic setting, astronomers have turned their radio telescopes toward the cold, dark molecular clouds that drift between the stars in incredibly distant galaxies. Within these ancient clouds, they hunt for a specific molecule, methanol. Think of methanol as a kind of cosmic tuning fork. Its structure, with a carbon atom, an oxygen atom, and 4 hydrogen atoms, causes it to vibrate and rotate in a very specific way. The light it absorbs and emits because of this motion creates a very precise pattern of spectral lines. And here's the crucial part. The exact spacing and position of these lines are exquisitely sensitive to the proton-to-electron mass ratio. If that ratio were different in the past, the methanol molecule's spectral fingerprint would be slightly distorted. Its lines shifted in a telltale pattern that cannot be explained by the expansion of the universe alone. When scientists point powerful instruments like the Atacama Large Millimeter Array in Chile at these faraway clouds, they are essentially looking at a fossil record of physics from billions of years ago. The light we see today left those galaxies when the universe was young. Several studies analyzing this ancient methanol light have reported a tantalizing hint. They suggest that the proton-to-electron mass ratio might have been minutely smaller in the distant past. We're talking about a change of just a few parts in 100,000 over billions of years, a shift so small it seems almost negligible. But in the precise equations of quantum physics, such a tiny drift is monumental. It would mean that the very building blocks of matter have been ever so slightly recalibrating themselves across cosmic history. The implications of this are staggering. If the proton-to-electron mass ratio were different, the very nature of reality would shift. Nuclear physics would change, altering how protons and neutrons bind together inside stars, potentially changing the way stars fuse hydrogen into helium and forge the heavier elements essential for planets and life. Chemistry itself would be different. The rates of reactions, the stability of complex molecules, even the very possibility of forming the long chains of carbon-based molecules that are the foundation of biology, all of it hinges on this precise mass ratio. A universe where this number is even slightly off might be a universe without the complex chemistry necessary for life as we know it. These findings are not yet settled science. The measurements are at the very edge of what is possible, and the scientific community continues to debate and verify the results. But the mere possibility is what drives the search forward. It has ignited a parallel effort in ultra-precise laboratory experiments here on Earth, where physicists use laser spectroscopy on trapped molecules to see if we can detect any change in this ratio happening right now in real time. This convergence of astronomy and experimental physics creates a powerful two-pronged attack on the question. We are simultaneously reading the universe's ancient diary in the light from distant quasars and watching the second hand on the cosmic clock with unimaginably precise instruments, all to answer one profound question: are the scales upon which we measure reality itself changing with time? But perhaps the most pressing and widely discussed clue in this cosmic mystery doesn't come from the spectral lines of distant atoms, but from a fundamental disagreement about the very pace of the universe's expansion. This is the Hubble Tension, a puzzle so stubborn it has divided cosmologists into camps and forced a re-examination of our most basic assumptions. The Hubble constant, named after the astronomer who discovered the universe is expanding, is arguably the most important number in cosmology. It tells us how fast the cosmos is stretching apart at the current time, and by extension, it allows us to calculate the age of the universe and predict its ultimate fate. For decades, we assumed there was one true value, and that as our measurements got better, we would simply converge on the right number. The reality has been the opposite. When we use what's called the distance ladder method, a meticulous process of measuring the brightness of certain stars and supernova in relatively nearby galaxies to calibrate distances and velocities, we get a specific, robust value for the Hubble constant. This is like measuring the expansion rate by looking at landmarks in our own cosmic neighborhood. But when we use the other primary method, which involves studying the faint afterglow of the Big Bang, the cosmic microwave background, we get a different answer. The CMB gives us a pristine snapshot of the infant universe, and by plugging its properties into our standard model of cosmology, we can predict what the Hubble constant should be today. These two methods, both exquisitely precise and conducted by brilliant teams, disagree by a small but statistically significant amount. It's as if you calculated the age of a tree by counting its rings and got one answer, but then calculated it by measuring its height and growth rate and got a consistently different result. This isn't a simple error, it's a fundamental tension that suggests something is missing from our model. This is where the idea of evolving physical laws enters the stage as a potential peacemaker. Our entire interpretation of the cosmic microwave background relies on the assumption that the laws of physics have remained perfectly constant for nearly 14 billion years. The equations we use to analyze that ancient light assume that the strength of gravity, the behavior of dark energy, and the nature of particles have not budged an inch. But what if that's not true? Imagine if the force of gravity was very slightly stronger in the early universe. This would have affected how quickly the first structures began to clump together, which would in turn change the subtle patterns we see in the CMB. If we were to rerun the calculations with a slightly different gravitational constant in the past, it might perfectly reconcile the predicted expansion rate with the one we measure locally. Alternatively, perhaps it's dark energy that isn't constant. Our standard model treats it as a fixed cosmological constant, but if its influence has been slowly growing or fading over time, that would dramatically alter the expansion history of the universe. A dynamic dark energy could have caused the universe to expand at a different pace in its youth than our current models assume, once again bridging the gap between the two conflicting measurements. The Hubble tension is more than just a technical disagreement. It's a beacon pointing toward potentially new physics. It highlights that our understanding of cosmic history is a story we've pieced together, assuming the rules never change. If that foundational premise is flawed, then this discrepancy isn't a problem to be solved within the old framework, but the first clue leading us to a new and more profound understanding, one where the universe's rulebook itself has a history waiting to be read. Now, if the Hubble tension gives us a hint that our cosmic rulebook might have a few unwritten amendments, then the story of dark energy suggests the entire rulebook could be a living document, subject to revision. For decades, the biggest surprise in cosmology was the discovery that the universe isn't just expanding, it's accelerating. Some mysterious repulsive force, completely invisible to our telescopes, is pushing galaxies apart faster and faster. We named this force dark energy, but naming something is not the same as understanding it. The simplest explanation, the one that fits most neatly into Einstein's old equations, is that dark energy is a constant, immutable energy inherent to the fabric of space itself, a cosmological constant. This idea offers a clean, elegant solution. It assumes that the strength of this dark energy, its push, has been exactly the same in every cubic centimeter of space for all of time. But what if that simplicity is an illusion? What if dark energy isn't a constant feature of the vacuum, but something far more dynamic? This is where the question of evolving constants takes on a truly cosmic scale. Theorists have proposed models where dark energy isn't a static force but a changing one. Imagine it not as a fixed setting on the universe's control panel, but as a dial that very, very slowly turns. In some of these models, dark energy is not a constant but a field, often called quintessence, a name evoking an ancient, elusive fifth element. This field could permeate all of space, but its energy density could gradually decrease over billions of years. Alternatively, it could interact with other forces, its strength waxing or waning in a cosmic dance we are only beginning to imagine. The implications of this are breathtaking. If dark energy's influence has changed over time, it would mean the acceleration of the universe is not a recent, sudden event but a process with a history. The fate of the cosmos would hang in the balance of this evolution. A dark energy that grows stronger could lead to a big rip, where the accelerating expansion eventually tears apart galaxies, solar systems, and even atoms themselves. A dark energy that fades away could allow gravity to eventually reassert its dominance, potentially leading to a big crunch. The very long-term destiny of everything is directly tied to whether this mysterious force is constant or not. This idea of a dynamic dark energy doesn't exist in a vacuum. It connects directly to the stability of the other fundamental constants. If the energy of the vacuum itself can evolve, could it be subtly influencing other forces? Some grand unified theories suggest that the strengths of all fundamental forces, including electromagnetism and the nuclear forces, were once unified in the extreme heat of the Big Bang and only took on their separate identities as the universe cooled. If dark energy is changing, it could be a sign that this process of separation isn't entirely finished, that these forces are still very subtly coupled together and evolving in concert. A weakening dark energy might be linked to a very slight strengthening of gravity over eons, or vice versa. This transforms our investigation from looking for isolated, drifting numbers to searching for a coordinated symphony of change across the entire laws of physics. The cosmological constant, which Einstein introduced as a fudge factor and then discarded, might not be a constant at all, but the most visible symptom of a deeper, more profound evolution happening at the very heart of reality. Understanding dark energy, therefore, becomes the master key to unlocking the ultimate question. Are the laws of physics the eternal, immutable commandments of the cosmos, or are they more like local ordinances, subject to change as the universe grows older and evolves into something new? But to truly stretch our imagination to the breaking point, we must venture into the realm of string theory, a framework so vast it redefines the very meaning of the word universe. Here, the idea of evolving constants isn't just a possibility, it's an inevitable feature of a much grander cosmic architecture. String theory suggests that the fundamental building blocks of reality are not point-like particles but unimaginably tiny, vibrating loops of energy. And these strings don't just dance in the three spatial dimensions we experience. They require extra, hidden dimensions of space, curled up into shapes so small we can't perceive them. The specific way these extra dimensions are folded, their topology and geometry, determines the laws of physics that emerge in our observable universe. The fine structure constant, the proton-to-electron mass ratio, even the strength of gravity, they aren't handed down from on high as fixed commandments. They are the consequences of this hidden dimensional origami, and if the shape of those dimensions can change, even slightly, then so too can our physical laws. This is where the concept explodes into its most breathtaking form, the multiverse. In this view, our entire cosmos, with its specific set of physical constants, is just one bubble in a frothing, infinite sea of universes. Each of these other universes could have its own unique configuration of those curled-up dimensions, and therefore its own completely different, equally valid set of physical laws. In some, the electromagnetic force might be so strong that atoms can't form, leaving a barren soup of particles. In others, gravity might be dominant, causing every universe to immediately collapse into a black hole. We simply happen to inhabit a rare bubble where the numbers are just right for galaxies, stars, planets, and life to emerge, a concept known as the Anthropic principle. But string theory pushes even further. It suggests that these constants might not even be permanently fixed within our own bubble. The vacuum of space itself might not be stable. Our universe could be in a false vacuum state, a valley of stability that isn't the true lowest energy state. A chance quantum fluctuation could someday cause a bubble of true vacuum to form and expand at the speed of light, rewriting the laws of physics in its wake in a cataclysmic phase transition. Less dramatically, the constants could be slowly drifting as the hidden dimensions gradually shift their shape over billions of years. This perspective completely transforms the question we've been asking. It's no longer just, are the constants changing? Instead, it becomes, how do they change? And what is the mechanism behind their evolution? Our universe's specific settings are no longer seen as eternal and fundamental, but more like the current weather pattern on a planet with a dynamic climate. They are a temporary configuration, a local set of bylaws in a cosmic metropolis teeming with different regulations. This isn't just a wild speculation. It provides a powerful theoretical backdrop that makes the search for varying constants not just reasonable, but essential. If string theory and the multiverse are correct, then the tiny drifts we might be detecting are not errors or anomalies. They are the first faint whispers from the higher dimensional geometry of reality itself, subtle clues that our cosmic bubble has a history and a future that is intimately connected to a far vaster and more exotic reality beyond our own. This astonishing fine-tuning of the universe's constants leads us directly to one of the most profound and debated concepts in modern cosmology, the Anthropic principle. At its heart, this principle offers a simple yet mind-bending observation. The reason we find the laws of physics so perfectly suited for life is because if they were even slightly different, we wouldn't be here to notice. It's a statement that feels almost like a tautology, but its implications are staggering, forcing us to confront the very nature of our existence and the possibility that our universe is not a random accident. Consider the forces that govern reality. If the strong nuclear force which glues atomic nuclei together were just a few % stronger, all the hydrogen in the early universe would have fused into heavier elements almost instantly. There would be no hydrogen left to fuel stars, no water to form oceans, and no possibility for life as we know it. If it were slightly weaker, elements wouldn't form at all, and the universe would be a boring soup of isolated particles. The same razor's edge applies to gravity. A tiny bit stronger, and the universe would have collapsed back on itself moments after the Big Bang. A fraction weaker, and matter would never have clumped together to form galaxies and stars. The expansion rate of the universe itself had to be exquisitely calibrated. Too fast and no structures form, too slow and everything collapses. This isn't just one lucky break, it's a countless series of them, a cosmic lottery that we somehow won. Now layer the possibility of evolving constants onto this picture, and the anthropic principle transforms from a static observation into a dynamic story. If the fundamental numbers can change, then perhaps our universe isn't just accidentally life-friendly. Perhaps it has, in some sense, become so. One compelling idea is that we are living in a particularly stable and hospitable era within a much longer cosmic cycle. Imagine the constants not as fixed points, but as dials that very slowly turn. For vast eons, the settings might be wildly inhospitable, producing universes that flash into existence and vanish without forming a single atom. But over trillions of years, perhaps the dials occasionally drift into a Goldilocks zone, a sweet spot where stars can ignite, planets can coalesce, and conscious beings can arise to look up at the night sky and wonder how it all works. In this view, our existence is tied to a specific chapter in a much longer biography of the cosmos. The alternative, and perhaps even more radical, explanation comes from the multiverse concept we touched on earlier. If an infinite number of universes exist, each with its own random set of physical constants, then it is no surprise at all that we find ourselves in one of the exceedingly rare ones where the numbers allow for our existence. We are not the purpose of the cosmos. We are simply the inevitable outcome of a statistical probability. If you roll the dice an infinite number of times, eventually you will get a universe that can ask why the dice landed that way. This perspective can feel humbling, even unsettling, as it suggests our universe is not special or designed, but merely one possibility among a near infinity of failures. But what if the truth lies somewhere in between? Some theoretical physicists speculate about a universe capable of a form of self-selection or self-adjustment. While it sounds like science fiction, the idea is that the presence of observers might somehow feed back into the laws that allowed them to emerge. This isn't about consciousness creating reality, but rather about the laws settling into a stable state that can sustain complex structures over long periods. It's a controversial idea, pushing the boundaries of what we consider science, but it highlights how deeply the anthropic principle challenges us. It forces a merger between the hard, quantitative data of physics and the deep, philosophical questions of why we are here at all. The principle doesn't provide easy answers, but it reframes the entire search for evolving constants. Finding evidence that the laws have changed wouldn't just be a discovery about physics. It would be a clue about our own place in a potentially vast and evolving cosmic landscape. a landscape where the conditions for life are not a permanent fixture, but a temporary and precious window of opportunity. So how do we move from grand theoretical speculation to hard, testable science? How do you actually measure something as abstract as the potential drift of a number that defines reality itself? The answer lies in a breathtaking combination of cosmic archaeology and laboratory wizardry, where scientists have devised ingenious methods to hunt for these subtle shifts across both space and time. One of the most powerful tools in this quest doesn't require looking into deep space at all, but rather involves staring intently at the hyper-precise ticks of atomic clocks here on Earth. These are not ordinary timepieces. They are perhaps the most accurate measuring devices ever created by humanity. They work by locking onto the natural, incredibly stable vibration of atoms, cesium or strontium atoms that oscillate between energy states with a regularity that dwarfs the rotation of planets or the swinging of pendulums. By comparing the ticks of two different types of atomic clocks over months or years, physicists can search for a telltale sign of drifting constants. For instance, a clock based on the vibration of a cesium atom might be sensitive to changes in the fine structure constant, while one based on a strontium atom reacts differently. If these two supremely accurate clocks begin to slowly disagree over time, it could be evidence that the fundamental physics governing their atomic ticks is itself changing. It's like having two perfect metronomes that have always been in sync. If you notice one starting to very gradually slow relative to the other, you have to question whether the very laws of rhythm are in flux. But to truly travel back in time, we must turn our gaze to the heavens. This is where astronomers become cosmic historians, using giant telescopes as time machines to peer into the distant past. As we discussed with quasars, these brilliant beacons of light from the early universe act as backlit screens. When their light passes through ancient clouds of gas, the atoms within those clouds imprint a unique absorption fingerprint onto the light spectrum. The exact positions of these dark spectral lines are dictated by the fundamental constants. By meticulously measuring these lines from objects billions of light years away and comparing them to the lines we see in laboratories today, researchers can effectively conduct a direct experiment on the physics of the ancient cosmos. They are comparing the universe's old handwriting to its new handwriting, looking for any subtle differences in the penmanship that might betray a change in the rules. This method provides a snapshot of what the constants were like billions of years ago, offering a crucial piece of historical data. Complementing this is the study of the cosmic microwave background, the faint afterglow of the Big Bang. This ancient light, which has been traveling for over 13 billion years, carries with it a frozen record of the universe's infancy. Tiny variations in its temperature and polarization patterns encode information about the physics of that primordial era, including the values of key constants that governed how matter and radiation interacted. By building sophisticated computer models of the early universe and comparing their predictions to the exquisitely detailed maps of the CMB from missions like Planck, cosmologists can perform a different kind of test. If the observed CMB patterns only make sense if certain constants had slightly different values in the past, it would be powerful, albeit indirect, evidence for their evolution. And the search doesn't stop there. Back in ultra-controlled laboratory settings, physicists are performing equally awe-inspiring experiments. They can trap single atoms or ions using electric and magnetic fields, holding them perfectly suspended in a vacuum. They then probe these isolated particles with lasers, measuring their energy transitions with unimaginable precision. By monitoring these transitions over long periods, they are effectively watching for any minute changes in the internal workings of atoms happening right now in real time. Other experiments study the vibrations of molecules with similar precision. as these motions are also exquisitely sensitive to constants like the proton-to-electron mass ratio. Each of these methods, atomic clocks, quasar spectroscopy, CMB analysis, and lab-based precision measurements, has its own strengths and weaknesses, but together they form a powerful, multi-pronged assault on one of physics' deepest questions. They represent humanity's collective effort to determine whether the foundations of our reality are the solid bedrock we've always assumed, or something far more dynamic and fascinating, shifting almost imperceptibly beneath the surface of our everyday experience. While astronomers peer across cosmic distances to read the universe's ancient diary, another group of scientists is conducting an equally profound investigation right here on Earth, using devices of such staggering precision that they can measure the potential drift of reality itself over the course of just a few years. These are not ordinary clocks. An atomic clock is a monument to human ingenuity, a machine that measures time by locking onto the natural, unwavering vibration of atoms themselves. Inside a vacuum chamber, isolated from the outside world's noise and vibrations, atoms like cesium or strontium are superheated into a gaseous state or trapped by lasers. Scientists then bathe these atoms in microwave or laser light, tuned to a frequency that causes the electrons to jump between two specific energy levels. This jump is the atom's natural resonance, its heartbeat, and it is phenomenally stable. A cesium atom, for instance, oscillates exactly 9,192,631,770 times per second. This isn't just a number, it is the very definition of a second in the International System of Units. The clock counts these oscillations, and in doing so, it creates the most regular, reliable pulse we have ever engineered. The true power of these clocks, however, isn't just in their incredible stability, but in their ability to be compared against one another. This is where the search for evolving constants comes alive. Researchers don't just use one type of atomic clock. They build different versions that rely on the hyperfine transitions of different elements, like cesium, strontium, or ytterbium. The crucial insight is that the tick rate of each type of clock depends on a slightly different combination of fundamental constants. For example, the oscillation of a cesium clock is more sensitive to the fine structure constant, which governs electromagnetism, while a clock based on the vibrations of a hydrogen atom might be more influenced by other quantum factors. Now imagine placing these two exquisitely precise clocks side by side in a perfectly controlled laboratory environment. You set them in perfect sync. According to all our standard theories, they should remain in lockstep forever, their ticks echoing in perfect unison because the laws of physics that govern them are unchanging. But if, over months or years of continuous measurement, scientists were to detect that one clock's ticks are very, very slowly beginning to drift out of sync with the others, it would be monumental. This tiny desynchronization wouldn't be a sign that one clock is broken. It would be potential evidence that the fundamental constants that dictate their respective rhythms are themselves changing. It would be as if two perfect metronomes, built to the same specifications and started at the same time, gradually began to disagree, forcing us to conclude that the very nature of rhythm had evolved. The sensitivity required for this experiment is almost beyond comprehension. We are talking about trying to detect a potential change of one part in a number with 18 zeros after it over the course of a single year. To achieve this, these clocks operate in environments that are more isolated than the depths of intergalactic space. They are shielded from the magnetic field of the Earth, kept at temperatures just a fraction of a degree above absolute zero, and protected from any vibration or external radiation that could disturb the atom's delicate dance. The lasers used to probe the atoms are so precise that their frequency is stable to within a few quintillionths of a percent. This isn't just timekeeping. It is the most precise experimental art form humanity has ever devised, pushing the very limits of what is measurable. What makes this terrestrial approach so complementary to the astronomical one is the timescale. Looking at quasars gives us a single, powerful snapshot of the universe's physics from billions of years ago. Atomic clocks, by contrast, provide a live, real-time feed. They are watching for changes happening right now in the present moment. A positive result from such an experiment would be immediately earth-shattering, providing a direct, incontrovertible measurement that the laws of physics are not constants, but variables in the ongoing story of our universe. Even a null result, finding no change at all over years of painstaking observation, is profoundly valuable. It places incredibly tight constraints on how fast any such change could possibly be occurring, ruling out entire classes of theoretical models and telling us that if the constants are drifting, they are doing so at a pace so glacial that it requires the patience of the cosmos itself to witness. To conduct this cosmic detective work, astronomers rely on some of the most powerful telescopes ever built, perched atop remote mountains where the air is thin and clear. Instruments like the Keck Observatory in Hawaii and the Very Large Telescope, or VLT, in Chile's Atacama Desert are the workhorses of this endeavor. Their massive mirrors, some over 8 meters across, act as enormous light buckets, gathering the faint, ancient photons that have traveled for more than half the age of the universe. But the real magic happens with the spectrographs attached to these giants, instruments with names like HIRES and ESPR-ESSO. These are not simple cameras. They are incredibly sophisticated machines that can split the incoming quasar light into a superbly detailed rainbow, a spectrum, and then measure the precise wavelength of every single dark absorption line with almost unbelievable accuracy. We're talking about being able to detect a shift in the position of these lines equivalent to the width of a human hair from a distance of 10 kilometers. This level of precision is what makes the search for varying constants even conceivable. However, achieving this is a Herculean task fraught with potential pitfalls. The entire process is a minefield of possible systematic errors that could easily mimic the signal of a changing constant. For instance, the temperature and pressure inside the spectrograph itself can fluctuate minutely, causing the instrument to expand or contract ever so slightly, which would shift the apparent position of all the spectral lines. To account for this, astronomers must constantly calibrate their instruments using known light sources, like thorium-argon lamps, which emit light at very specific, stable wavelengths. But even this isn't foolproof. Another enormous challenge is the possibility of astrophysical contaminants. The ancient gas clouds the light passes through might not be as simple as we assume. They could contain different isotopes of elements than we find today, or be at a different temperature or pressure, both of which could alter the absorption pattern in a way that looks exactly like a change in a fundamental constant. It's the ultimate game of ruling out every other possible explanation. Researchers must analyze dozens, even hundreds of quasars, looking for a consistent pattern of shift that points toward a real change in the laws of physics rather than a local anomaly or a measurement artifact. Each new quasar observation is another data point on a vast cosmic graph, another piece of evidence in a trial where the defendant is reality itself. The painstaking, meticulous nature of this work, often requiring years of observation and analysis for a single conclusive paper, is a testament to the rigorous standards of science. It's a frontier where patience is as important as technology, and where every claim of discovery is met with a healthy dose of skepticism until it can be independently verified. This relentless pursuit of certainty, this refusal to accept an easy answer, is what separates a groundbreaking discovery from a simple anomaly, ensuring that if we ever do find proof that the constants are changing, we can be truly confident that the universe itself is whispering its secrets to us. While atomic clocks and quasar spectroscopy search for changes happening now or in the more recent cosmic past, there exists an even more ancient and pristine time capsule that allows us to peer back to the very dawn of time itself. This is the cosmic microwave background, or CMB, often described as the afterglow of the Big Bang. Imagine the universe not as the vast, dark expanse of galaxies we see today, but as a searing, opaque fog of plasma, a hot and dense soup of particles and energy. Then, about 380,000 years after the initial moment of creation, the universe had expanded and cooled just enough for a monumental transition to occur. Electrons combined with protons to form the first neutral hydrogen atoms. In that instant, the cosmic fog lifted. Light, which had been trapped, bouncing endlessly between particles, was suddenly set free to travel across the cosmos. That first flash of liberated light is what we detect today as the CMB. It has been stretching and cooling for over 13 billion years, its waves lengthened by the expansion of the universe until it now reaches us as a faint microwave static, a cold whisper from the infant cosmos permeating all of space. This ancient light is far more than a simple relic. It is a detailed baby picture of the universe, encoding a wealth of information about its physical state and composition at that primordial moment. Sophisticated space-based observatories, most notably the European Space Agency's Planck mission, have spent years mapping this faint glow with breathtaking precision. They have produced an all-sky map of tiny temperature variations, minute fluctuations where some patches of the early universe were ever so slightly denser and hotter than others. These tiny ripples are the seeds of all future structure, the gravitational wells from which galaxies and clusters would eventually grow. The patterns in these ripples are not random. They hold precise information about the contents of the universe, the amount of ordinary matter, the mysterious dark matter, and the influence of dark energy. But most importantly for our quest, these patterns are exquisitely sensitive to the fundamental laws of physics that govern the universe at 380,000 years old. The physics of how sound waves propagated through that primordial plasma, how gravity tried to clump matter together, and how radiation pressure fought back. All of this is frozen into the statistical properties of the CMB's temperature and polarization patterns. As scientists have analyzed this data with ever-increasing sophistication, certain subtle anomalies have emerged, quirks in the data that don't quite align with the predictions of our standard model of cosmology, known as lambda CDM. This model assumes the laws of physics have remained perfectly constant. For instance, the large-scale fluctuations in the CMB appear to be slightly less intense than the model predicts, and there are curious asymmetries in the average temperatures between one half of the sky and the other. One of the most intriguing potential anomalies involves the inferred ratio of baryons, the particles that make up ordinary matter, to photons, the particles of light. This ratio is a crucial number set very early in the universe's history, and it directly influences the characteristics of the sound waves imprinted on the CMB. If this ratio seems inconsistent with other cosmological measurements, it could be a monumental clue. It might suggest that the constants which governed nuclear processes in the first few minutes of the universe, during the period of Big Bang nucleosynthesis when the first light elements were forged, were subtly different from their values today. A slightly different strength of the nuclear forces could have altered the efficiency of those first nuclear reactions, changing the amount of helium and deuterium produced, and consequently, the final baryon-to-photon ratio we infer from the CMB. Unraveling this potential clue is a task of monumental complexity. The CMB signal we measure today is not a perfectly clean recording. It has been subtly altered during its 13 billion-year journey to us. The gravitational influence of intervening galaxy clusters can slightly distort the light's path, an effect called gravitational lensing. Our own galaxy emits microwaves that must be carefully subtracted from the data. Isolating the pristine, primordial signal from these later contaminating effects requires building incredibly sophisticated statistical and physical models. Scientists must run vast computer simulations of the universe's evolution, testing what would happen to the CMB patterns if, for example, the fine structure constant or the gravitational constant had a different value in that ancient epoch. They are essentially playing a high-stakes game of cosmic what-if, tweaking the fundamental parameters in their simulations to see if they can produce a virtual CMB that matches the curious anomalies we actually observe. This makes the cosmic microwave background not just a snapshot, but a rigorous experimental testbed. It offers a completely independent avenue from quasar studies to ask the same profound question, probing the constancy of physics at a time when the universe was a mere infant, long before the first star or galaxy had even formed. So if the evidence from quasars, atomic clocks, and the cosmic microwave background is pointing toward something deeper, what could possibly be the mechanism behind these potential changes? How could a fundamental number seemingly etched into the fabric of reality actually be capable of drifting? This brings us to one of the most fascinating and elegant theoretical ideas in modern cosmology, the concept of scalar fields. Think of a scalar field as an invisible energy field that fills all of space, a bit like an intangible ocean whose currents and tides are completely undetectable to our senses. Unlike the fields we're more familiar with, like the magnetic field that pulls a compass needle, a scalar field has no direction. It has only a value, a single number that can vary from place to place and, crucially, from time to time. It is this very property that makes scalar fields the perfect candidate for being the engine behind evolving constants. The most famous example of a scalar field in physics is the Higgs field, which is responsible for giving elementary particles their mass. But what if there are other, much lighter and more subtle scalar fields still waiting to be discovered? This is where the idea gets truly exciting for cosmologists. Imagine a new, undiscovered scalar field that is weakly coupled to the other forces of nature. As this field evolves over the billions of years of cosmic history, its changing value could very gently tweak the strength of electromagnetism or gravity, causing the constants we measure to drift ever so slightly. In this view, a constant like the fine structure constant isn't a fundamental, immutable number at all. Instead, it's what physicists call an effective constant, a value that emerges from the interaction of particles with this underlying cosmic field. If the field changes, the constant changes with it. This transforms our understanding from a universe with fixed rules to a universe with a dynamic control panel, where the dials are turned by the slow, grand evolution of these hidden fields. This idea finds its most powerful application in one of the biggest mysteries we've discussed, dark energy. The Standard Model treats dark energy as a cosmological constant, a fixed feature of empty space. But many theorists find this unsatisfying. Why should the energy of the vacuum be this specific, unchanging value? An alternative proposal is that dark energy is not a constant at all, but a dynamic scalar field, often given the poetic name quintessence. hearkening back to the ancient idea of a fifth element beyond Earth: air, fire, and water. In quintessence models, the energy density of this field can slowly decrease over time. This would mean that the repulsive force causing the universe's acceleration wasn't always the same and might not be the same in the future. But the implications go even further. If such a quintessence field exists, it wouldn't exist in isolation. It would inevitably interact with the fields that govern matter and radiation. A very slight coupling between the quintessence field and the electromagnetic field, for instance, would mean that as the quintessence field evolves and dark energy changes, it would also impart a tiny, continuous change on the fine structure constant. This provides a beautifully unified framework. A single, dynamic scalar field could potentially explain both the accelerating expansion of the universe and the tantalizing evidence for varying constants, linking two of the deepest puzzles in cosmology into one elegant package. Of course, a good theory must do more than just explain existing puzzles. It must also make new, testable predictions. This is where scalar field models truly shine. They don't just suggest that constants change, they predict how they should change. Different models propose specific relationships between the observed drift of a constant and the expansion history of the universe. For example, one model might predict that the fine structure constant should have been changing more rapidly during certain cosmic epochs, like during the period of intense dark energy domination. This gives astronomers a clear roadmap for their observations. By meticulously measuring the apparent variation of constants at different distances, and therefore different look-back times, they can check to see if the pattern of drift matches the predictions of a particular scalar field model. It turns the search from a simple, "is it changing?" into a more nuanced, "what is the functional form of that change?" A successful match would be incredibly powerful evidence, not just for varying constants, but for the existence of an entirely new cosmic field that has been shaping the evolution of the universe since its earliest moments. This transforms the quest from a controversial anomaly hunt into a direct test of new physics, guiding the next generation of telescopes and experiments in their mission to decode the deepest workings of reality. But to truly understand the potential for change at the most fundamental level, we must venture into the most extreme and mysterious domain of all, the realm of quantum gravity. This is the final frontier of theoretical physics, a place where our current understanding of the universe simply shatters. We have two incredibly successful theories: quantum mechanics, which exquisitely describes the world of the very small, and general relativity, which masterfully explains gravity and the cosmos at large. The problem is, these two theories are fundamentally incompatible. They speak different mathematical languages and make contradictory predictions when forced to meet. This violent clash occurs at an almost unimaginably tiny scale known as the Planck length, a distance so small that if you enlarged an atom to the size of the observable universe, the Planck length would be about the height of an average tree. At this incomprehensible scale, the smooth, continuous fabric of spacetime predicted by relativity is thought to break down into a seething, chaotic foam, a bubbling quantum froth where space and time themselves lose all meaning, fluctuating wildly and giving rise to virtual particles that pop in and out of existence. It is here, in this turbulent underworld of reality, that our most cherished constants might find their true origin and their potential for change. Our current laws of physics, with their fixed numbers like the fine structure constant, are what physicists call effective field theories. They are not the ultimate fundamental laws. They are incredibly accurate and powerful approximations that work perfectly in the low-energy, large-scale world we inhabit. They are the rules of the game for our everyday reality. But just as the rules of chemistry emerge from the deeper rules of quantum physics, our constants might themselves emerge from even deeper principles operating at the Planck scale. Think of it like watching a movie on a screen. At a distance, the picture appears smooth and continuous, following the clear laws of storytelling and motion. But if you press your nose against the screen, you see that this reality is actually composed of countless individual, discrete pixels flashing on and off. The smooth motion is an illusion created by the collective behavior of these tiny, separate parts. Quantum gravity theories propose that space-time itself might be pixelated in a similar way. Theories like loop quantum gravity and causal dynamical triangulation offer mathematical frameworks for this pixelated reality. They propose that space is not smooth and continuous, but is woven from tiny, finite loops or built from minuscule geometric building blocks like a cosmic Lego set. In these models, the familiar dimensions of space and time emerge from the connections and interactions between these fundamental units. This has a breathtaking implication for the constants of nature. In a universe with discrete spacetime, the constants we measure might not be fundamental properties handed down from on high. Instead, they could be collective, statistical properties, the average outcome of trillions upon trillions of underlying quantum events happening at the Planck scale. A simple analogy is the temperature of a gas. We can measure a single temperature for the whole gas, but that temperature isn't a fundamental property of any one air molecule. It emerges from the frantic, chaotic motion of all the molecules combined. In the same way, the speed of light or the strength of gravity could be the emergent, average result of the frenetic quantum geometry of spacetime. If this is true, then the door is swung wide open for these constants to vary. If the pixels of spacetime are dynamic and fluctuating, then the average values that emerge from them could also slowly drift over cosmological timescales. The constants would be stable in our current low-energy epoch simply because the average has settled into a steady state, much like the temperature of a room appears constant even though the air molecules are in constant motion. But over billions of years, as the universe expands and cools, the fundamental nature of this quantum spacetime foam could very gradually evolve, leading to a correspondingly gradual evolution in the effective constants we measure. Furthermore, some approaches to quantum gravity, like string theory, suggest there are additional spatial dimensions curled up at these tiny scales. The size and shape of these hidden dimensions directly determine the values of the constants in our observable four-dimensional world. If these compact dimensions can change their shape over time, a process known as modular stabilization, then the laws of physics in our universe would change along with them. Exploring quantum gravity, therefore, is not just an academic exercise to unify physics. It is a direct investigation into the very nature of physical law, asking whether the bedrock of our reality is permanent granite or something more like sandstone, seemingly solid but ultimately subject to the slow, erosive forces of deep time and deeper physics. But this incredible search for a shifting cosmos is perhaps the most difficult detective story ever told, precisely because the clues we're looking for are so vanishingly small, and the crime scene is the entire universe. Imagine trying to measure the width of a human hair from a distance of 10 kilometers, and then being certain that any tiny change you see isn't caused by the heat of the sun warping your ruler, or a gentle breeze nudging your measuring device. That's the scale of the challenge physicists face. The potential drift in a fundamental constant over billions of years might be a change of just a few parts in a million, or even a few parts in a billion. Teasing that signal out from the cacophony of the cosmos requires not just incredible precision, but an almost paranoid level of vigilance against countless sources of error that could lead us astray. These are not mistakes in the traditional sense. They are systematic biases, subtle effects that can perfectly mimic the signal of a changing constant without any real change having occurred at all. Consider the monumental task of quasar spectroscopy. We assume that the atomic absorption lines we see in the distant universe are caused by the exact same elements we have in our labs today. But what if that's not entirely true? The clouds of gas these ancient lights pass through could have a slightly different chemical composition. Perhaps certain isotopes, heavier or lighter versions of the same element, were more common billions of years ago. An atom with an extra neutron in its nucleus will absorb light at a very slightly different wavelength than its more common cousin. If we don't account for that, a cloud enriched in a particular isotope could produce a shifted spectral line that looks for all the world like a change in the fine structure constant, when in reality, it's just a different blend of atoms. It's like a detective finding a fingerprint at a crime scene and assuming it's from the suspect, when it might actually be from a visitor who was there the day before. Then there's the instruments themselves. The spectrographs attached to the world's largest telescopes are miracles of engineering, but they are not perfect. Minute changes in temperature or air pressure inside the instrument can cause its metal and glass components to expand or contract by microscopic amounts. These tiny movements can shift the apparent position of a spectral line on the detector, creating a false signal of change. To combat this, astronomers constantly bathe their instruments in the light of calibration lamps, which emit light at known, stable wavelengths. They use these lamps to create a map of any instrumental drift, painstakingly subtracting it from their cosmic data. But what if the lamp itself has a hidden instability? It becomes a dizzying hall of mirrors, where every tool used to verify another tool must itself be verified by something else. Even the Earth's atmosphere, which these magnificent telescopes must peer through, is a source of noise. The blanket of air around our planet acts like a shifting prism, bending and blurring the light from distant quasars. Advanced adaptive optics systems can correct for this in real time, using lasers to create artificial guide stars and deformable mirrors to cancel out the atmospheric shimmer. But no correction is ever 100% perfect. Faint, residual effects can still leave their imprint on the data, adding another layer of complexity to an already Herculean task. And we haven't even left our own galaxy yet. Interstellar dust within the Milky Way can also redden the light from distant quasars, an effect that must be meticulously modeled and removed to ensure the observed shifts are truly cosmological in origin. This is why a single measurement, no matter how tantalizing, is never enough to convince the scientific community. The only path forward is a relentless campaign of cross-checking and independent verification. Researchers must observe the same quasar with different telescopes and different instruments. They must hunt for the same potential drift in multiple chemical elements, each of which responds to a changing constant in a unique way, providing a distinct fingerprint that is much harder to fake with systematic error. They combine their quasar data with constraints from the cosmic microwave background and with the mind-boggling precision of laboratory atomic clocks, building a web of evidence that either supports or contradicts the idea of change. This process is slow, meticulous, and often frustrating. It is a powerful safeguard against the very human desire to make a monumental discovery. It ensures that if we ever do receive a confirmed signal that the constants are drifting, it will be because the universe is truly speaking to us, and not because we were merely hearing the echo of our own instruments. This rigorous, skeptical process is not a barrier to discovery. It is the very foundation of trust that makes any eventual discovery truly profound. For centuries, our entire conception of reality has been built upon a foundation of permanence. We've believed that the universe operates according to a set of eternal, unchanging laws, a fixed cosmic constitution that is the same everywhere and for all time. This view paints the cosmos as a magnificent but static machine, ticking along according to rules that were set in stone at the moment of creation. It offers a comforting sense of order and predictability, a universe where the same cause will always produce the same effect, and where the fundamental truths we discover today will hold true tomorrow and 1 billion years from now. But what if this foundational belief is an illusion? The possibility that the laws of physics themselves might be evolving doesn't just add a new chapter to a science textbook. It strikes at the very heart of our philosophical understanding of existence, reality, and our place within it. If the constants of nature are drifting, then the universe is not a static machine. It is more akin to a living, breathing, evolving organism. This perspective resonates deeply with a school of philosophical thought known as process philosophy, which argues that change and becoming are the fundamental features of reality, not being and permanence. Thinkers like Alfred North Whitehead proposed that the universe is not a collection of static objects but a complex web of processes and events, all interrelated and in a constant state of flux. In this view, what we perceive as stable objects are actually slow-moving processes, and what we call laws are simply deeply ingrained habits of nature. The idea of evolving constants fits this worldview perfectly. It suggests that the universe's habits themselves can change over immense timescales, that reality is not fixed but is an unfolding story, a continuous creation where the very rules of the narrative are being written as we go along. This transforms our home from a cold, clockwork mechanism into something far more dynamic and, in a way, more alive. This shift from a universe of being to a universe of becoming forces us to confront profound questions about the nature of scientific knowledge itself. Science has always sought to discover the eternal, objective truths of the cosmos. But if the laws are changing, then our most brilliant theories are not timeless revelations. They are merely temporary descriptions, incredibly accurate for our current cosmic era, but potentially irrelevant in the distant past or future. This doesn't devalue science. Instead, it historicizes it. It means that our scientific models are snapshots of a moving target, a local map of reality valid for a certain time and place within a much grander and more dynamic cosmic history. The quest for a final theory of everything might need to be reimagined not as the search for a single, unchanging set of equations, but as the discovery of the meta-laws, the rules that govern how the apparent laws themselves change and evolve over time. Furthermore, the potential mutability of physical law challenges our deepest notions of causality and time. Our entire understanding of cause and effect is predicated on the assumption that the rules linking them are stable. But if the strength of gravity or the charge of an electron were different in the past, then the chain of causality that led to our present universe becomes a path that could not be retraced with perfect certainty. The past becomes a slightly foreign country that operated under different regulations. This also infuses time with a new level of reality and directionality. In a static universe, time is often seen as a mere parameter, a coordinate on a graph. But in a universe with evolving laws, time has a true arrow not just because of entropy, but because the fundamental nature of reality itself is different at one end of time than it is at the other. The universe has a genuine history of becoming, not just a history of events happening on a static stage. Ultimately, this line of inquiry begins to blend rigorous science with deep metaphysical wonder. It pushes us to ask whether the universe could possess a kind of mind-like capacity for self-adjustment and evolution. This isn't to suggest a conscious, anthropomorphic God, but rather a universe with an inherent teleology or a tendency to complexify and create conditions for novelty and life. If the constants have drifted into a life-friendly Goldilocks zone, was this a random accident, or does it reflect a deeper principle of nature? The idea of evolving laws opens a door to considering that the universe might not be a passive arena but an active participant in its own development, a concept that moves us from a purely mechanical model to one that is far more organic and perhaps even creative, forever challenging our assumptions about where the boundary lies between the physical world and the realm of mind and meaning. History offers us a powerful mirror when we confront ideas that seem to upend our understanding of reality. Time and again, a radical shift in our cosmic story has been met not just with scientific debate, but with deep cultural and philosophical resistance. When Copernicus suggested the Earth was not the center of the universe, it wasn't merely an astronomical correction. It was a demotion that challenged the entire medieval worldview, which placed humanity at the heart of a divine creation. This geocentric model was woven into the fabric of religion, art, and philosophy, and to question it was to question the very order of God's universe. Galileo's subsequent persecution by the Church wasn't just about the motion of planets. It was a defense of a complete cosmic narrative that gave meaning and structure to human life. Similarly, when Einstein introduced a universe where time was relative and space could warp, it was initially dismissed by some as mere mathematical fiction, too bizarre and counterintuitive to be accepted. These weren't just scientific disagreements, they were moments of profound cultural anxiety, where the familiar ground of reality seemed to shift beneath society's feet. The potential discovery that the laws of physics themselves are not eternal would represent the next great step in this humbling journey. It would be a paradigm shift on a scale we haven't seen in centuries. For generations, we have been taught that the laws of nature are the ultimate fixed point, the unwavering rules that govern everything from the atom to the galaxy. This idea provides a foundation of certainty, not just for science, but for our entire modern worldview. Our technology, from GPS satellites to nuclear power, is built on the unwavering assumption that these constants are, well, constant. The suggestion that they might be fluid challenges the bedrock of predictability upon which we've built our civilization. It's not hard to imagine how this could ripple through our culture, creating new tensions between scientific discovery and established beliefs. Some religious interpretations, for instance, that see physical laws as a direct reflection of a constant and unchanging divine order, might find this new concept deeply disruptive. It could force a re-evaluation of theological doctrines in much the same way that evolutionary biology did, prompting a new dialogue between science and faith about the nature of a potentially evolving creation. Yet, history also shows us our remarkable capacity for adaptation. While initially disruptive, each cosmic revolution has ultimately expanded our sense of wonder and our place in the cosmos. The heliocentric model, once feared, gave us a grander vision of a solar system. The discovery of an expanding universe revealed a cosmos with a history and a beginning. We didn't lose meaning, we found new, more profound layers of it. If our current laws are provisional, it doesn't mean that science has failed or that reality is arbitrary. Instead, it would reveal a universe that is even more dynamic, creative, and awe-inspiring than we ever imagined, a cosmos that is not just in time, but is itself evolving with time. This perspective could fundamentally change how we teach science. Instead of presenting physics as a set of dead, final facts carved in stone, education could focus on the living, breathing process of discovery. It could tell the story of our evolving understanding, encouraging students to see themselves as part of that ongoing journey of questioning and exploration. By looking at these past transitions, we see a pattern: initial shock and resistance, followed by a gradual integration of the new idea into a richer, more complex, and ultimately more beautiful tapestry of understanding. This long tradition of cosmic curiosity, of pushing at the boundaries of what we think we know, is not a bug in the human character. It is its most magnificent feature, preparing us to meet the next great revelation not with fear, but with inspired wonder. While our current telescopes and atomic clocks are already performing feats of measurement that would have been unimaginable just a generation ago, the most powerful tools for this investigation are still on the horizon, poised to revolutionize our view of the cosmos. The next decade will be a golden age for observational astronomy, driven by a new class of instruments designed to see further and with greater clarity than ever before. Leading this charge is the James Webb Space Telescope, which has already begun its mission 1,000,000 miles from Earth. Unlike Hubble, which primarily sees invisible and ultraviolet light, Webb is an infrared telescope, and this is its superpower. The expansion of the universe stretches the light from the most distant objects into the infrared part of the spectrum, making Webb the perfect time machine to study the era of the first stars and galaxies. For our search, this means Webb can analyze the spectral fingerprints of elements in those ancient gas clouds with a sensitivity and resolution that was previously impossible. It can peer into the chemical makeup of the universe when it was only a few 100 million years old, looking for those subtle shifts in absorption lines that could indicate a different value for the fine structure constant, but with a level of precision that may finally settle the long-standing debates sparked by ground-based telescopes. But the revolution doesn't stop in space. Here on the ground, an absolute behemoth is taking shape on a mountaintop in Chile. The Extremely Large Telescope, or ELT, is a project so ambitious it seems to border on science fiction. Its main mirror is an astonishing 39 meters across, a colossal eye composed of nearly 800 individual hexagonal segments that will gather more light than all of the existing large telescopes on Earth combined. This immense light-gathering power is only part of the story. The ELT will be equipped with a new generation of spectrographs that are themselves marvels of optical engineering. Instruments like ESPRESSO will be able to measure the redshift of distant quasars and thus the potential drift of constants, with a precision that is an order of magnitude better than anything we have today. Where current data might hint at a possible anomaly, the ELT could provide a definitive, unambiguous signal, effectively allowing us to create a high-resolution movie of the universe's chemical evolution and watch for any inconsistencies in the laws of physics playing out across billions of years. It will be like upgrading from a standard-definition television to an 8K ultra-high-definition screen, details we could only guess at before will suddenly snap into sharp, undeniable focus. Simultaneously, the laboratory side of this search is undergoing its own quantum leap. The atomic clocks we discussed are not standing still, they are evolving into even more precise and exotic forms. The next generation of clocks moves beyond atoms to nuclei. Nuclear clocks would use the transition of a single thorium nucleus as their pendulum, a vibration that is far more resistant to external perturbations like temperature and magnetic fields than the electron transitions in atomic clocks. A nuclear clock could be up to 100 times more precise than the best atomic clocks of today. This isn't just an incremental improvement. It's a transformative leap that would allow scientists to search for the present-day drift of constants with almost unimaginable sensitivity. If the fine structure constant is changing today, these clocks would detect it within a matter of months or years, providing a real-time confirmation that would rock the foundations of physics. Alongside these, new quantum sensors that use entangled particles can take measurements that bypass the standard quantum limit, squeezing more information out of every observation and further reducing the uncertainty in our experiments. And the search extends beyond light and atoms. The nascent field of gravitational wave astronomy, which opened a completely new window on the universe with the detection of ripples in spacetime, will also play a crucial role. Future space-based observatories like the Laser Interferometer Space Antenna, or LISA, will detect gravitational waves from the mergers of supermassive black holes, events that have been happening since the universe was young. The characteristics of these waves depend on the laws of gravity that govern their creation. By comparing waves from ancient events with those from recent ones, cosmologists can test whether the strength of gravity itself has been constant over time. These diverse approaches, from the immense scales of galaxy surveys to the microscopic vibrations of a single nucleus, create a powerful, multi-pronged strategy. We are no longer relying on a single method or a lone dataset. We are building a comprehensive network of evidence that will either converge on a stunning new reality of a dynamic cosmos or firmly cement our current laws as the eternal, unchanging bedrock of existence. The answer, after centuries of questioning, is finally within our grasp. Imagine the monumental task facing a cosmologist today. A single night of observation on a telescope like the VLT can produce a terabyte of data on distant quasars, each spectrum a dense forest of thousands of absorption lines that must be measured with nanometer precision. The cosmic microwave background maps from the Planck mission contain over 50 million pixels, each with associated temperature and polarization data. This is a deluge of information so vast that no human, or even a team of humans, could possibly analyze it all by hand in a lifetime. For decades, the search for subtle clues like varying constants was limited not just by the power of our telescopes, but by the capacity of our own brains to process the information they collected. We were like detectives with a mountain of evidence but no way to read most of the pages. This is where a new, revolutionary partner enters the investigation: artificial intelligence. Machine learning algorithms are now being trained to become expert cosmic archaeologists. They can ingest millions of quasar spectra, learning to identify the unique fingerprint of specific elements like iron, magnesium, or silicon with a speed and consistency no human eye could ever match. But their true power lies not in simple identification, but in pattern recognition on a grand scale. A human researcher might focus on a handful of the strongest, cleanest absorption lines in a spectrum. An AI, however, can analyze every single line, no matter how faint, across hundreds of thousands of different spectra simultaneously. It can cross-reference the apparent shifts in iron lines with those in magnesium, looking for the specific, consistent pattern that would indicate a true change in the fine structure constant, as opposed to random noise or some local astrophysical effect. These algorithms are designed to be blind to human biases. They don't have a preferred theory or a hoped-for outcome. They simply sift through the cosmic data with inhuman patience, searching for the faint statistical whisper of a signal that could rewrite the laws of physics. This computational power is transforming the entire scientific process. In the past, a theorist might develop a complex model suggesting how the fine structure constant could change over time. Testing that model against real data would be a painfully slow process, requiring months of manual analysis on a small subset of available observations. Now, with AI, that same theorist can unleash their model against the entire historical archive of quasar data from a dozen different telescopes in a matter of days. The AI can run millions of simulations, comparing the predicted pattern of spectral shifts from the model against the actual, observed universe, and provide a statistical confidence level that tells us how well the theory fits reality. This accelerates the search from a ponderous walk to a sprint, allowing scientists to test and discard ideas rapidly, homing in on the few models that might actually explain what we see. The role of AI extends far beyond just analyzing light from quasars. It is also crucial for cleaning up the data itself. Remember the challenge of systematic errors, the minute temperature changes in a spectrograph or the subtle distortions caused by our own atmosphere. Machine learning models are exceptionally good at learning what these instrumental artifacts look like. They can be trained on calibration data to recognize the specific fingerprint of the telescope itself, and then subtract that signal from the cosmic data, leaving behind a much cleaner and more reliable picture of the distant universe. It's like having a restorer meticulously clean an ancient painting, carefully removing centuries of grime and varnish to reveal the artist's original brushstrokes underneath. By applying this AI-powered cleaning process, astronomers can be far more confident that any shifts they detect are truly from the cosmos and not from their own machinery. This partnership between human intuition and artificial intelligence is creating a new paradigm for discovery. The human scientist provides the creative spark, the big questions, and the theoretical frameworks. The AI provides the brute force computational power and pattern recognition capabilities to test those ideas against the vast, messy, and beautiful complexity of the real world. Together, they form a team capable of tackling questions that were once thought to be unanswerable. As our telescopes grow larger and our datasets swell to even more unimaginable sizes, this AI partnership will become not just helpful but essential. It is the key that unlocks the secrets hidden within the light of ancient stars, transforming that light from a passive record of the past into an active conversation with the cosmos about the very nature of its own laws. Now imagine a high school physics classroom, not in some distant future, but perhaps just a decade from now. The familiar chart of fundamental constants might still be hanging on the wall, but the lessons surrounding it would be profoundly different. Instead of presenting these numbers as eternal, unquestionable truths handed down from on high, the teacher would frame them as the current settings of the universe, the values we measure in our particular cosmic era. This shift from teaching physics as a set of fixed laws to presenting it as a grand, unfolding narrative of cosmic change would be one of the most exciting transformations in education, turning a subject sometimes seen as static into a living, breathing story of discovery. The very goal of science education would evolve, moving beyond just memorizing formulas to fostering a deep, flexible curiosity about how our understanding itself evolves. To make such an abstract concept tangible for students, educators would need powerful new analogies, moving beyond the traditional clockwork universe to something more organic. They might compare the cosmos to a giant, ancient tree. We can measure the width of its rings today and understand its current state of growth, but we also know that the tree was once a tiny sapling, and its internal processes have changed and adapted over its long lifetime. The constants of nature could be like the tree's rate of growth, mostly stable from season to season, but potentially varying over centuries in response to a changing environment. Or consider the shifting of the seasons. We experience spring, summer, fall, and winter as a predictable cycle, yet the Earth's climate has undergone enormous changes over millennia, with ice ages and warm periods. The laws of physics could be like the climate, stable on the scale of a human lifetime but slowly evolving over cosmic timescales. These metaphors wouldn't just make the science accessible, they would make it relatable, connecting the vast cosmos to the familiar cycles of life students see around them every day. This new approach would naturally weave together science, history, and philosophy, breaking down the artificial barriers between disciplines. A curriculum on gravity wouldn't start just with Newton's apple, but with Aristotle's vision of a perfect, unchanging celestial realm, moving through Einstein's revolutionary model of dynamic spacetime, and ending with the modern puzzle of the Hubble tension and the question of whether gravity itself might be changing. Students would learn that Isaac Newton himself believed God might occasionally need to intervene to keep the solar system stable, a historical footnote that reveals the deep-seated human anxiety about a universe that might not be perfectly self-regulating. By seeing how even our greatest scientific minds have grappled with the idea of cosmic constancy, students would understand that science isn't a dusty collection of facts, but a dynamic human endeavor, a continuing conversation full of debates, dead ends, and dazzling breakthroughs. This teaches a crucial lesson that not knowing the final answer is not a failure, but the very engine of scientific progress. Ultimately, preparing students for a universe where the fundamental rules might be in flux is about much more than just teaching new physics. It's about equipping them with a mindset of adaptability and intellectual humility for a world of constant change. The career paths many of them will follow haven't even been invented yet, and the technologies they'll use will be based on scientific principles we are only now beginning to glimpse. By embracing the idea that even the deepest laws might be dynamic, we foster a generation of thinkers who are comfortable with uncertainty, who are critical consumers of information, and who see themselves not as passive learners of established knowledge, but as active participants in its ongoing creation. They would be the ones designing the experiments to test these very ideas, perhaps using technologies we can't yet conceive, to answer the question we are asking today. This transforms education from a process of transmission to one of inspiration, ensuring that the next great discovery about our evolving cosmos doesn't just come from our isolated team of researchers, but from a whole generation raised to see the universe not as a fixed monument, but as a story that is still being written and in which they themselves can play a part. While the idea of shifting physical constants might feel like a problem for cosmologists debating the distant past, it forces us to confront a startlingly practical question about our own future. Every piece of advanced technology we rely on, from the smartphone in your pocket to the global network that powers our economy, is built upon a foundation of unwavering physical law. The entire system of global positioning satellites, or GPS, functions because we know the precise speed of light and the exact behavior of atomic clocks on satellites moving at significant fractions of that speed. If those constants were to drift over millennia, the delicate synchronization that allows a phone to pinpoint its location within meters would slowly degrade into useless noise. The same is true for the immense computational power driving our world. The semiconductor industry depends on the immutable quantum properties of electron silicon to design ever smaller transistors. A change in the fine structure constant could alter the very band gaps that make this possible, rendering future chip designs inoperable and stalling the engine of digital innovation. Even our energy infrastructure, particularly nuclear power and the emerging field of fusion research, is predicated on deeply understood nuclear cross-sections and the strength of the strong force that holds atomic nuclei together. A universe where the rules are in flux is a universe where our technological civilization might eventually find its entire operating manual slowly becoming obsolete. This long-term perspective introduces a profound ethical dimension to what might seem like abstract research. It shifts the motivation for fundamental science from one of pure curiosity to one of profound responsibility. Investing in experiments that test the constancy of nature is not merely an academic exercise, it is a form of cosmic due diligence. By understanding the potential for change, we are essentially taking out an insurance policy for future generations. The ethical imperative is to be good ancestors, to use our brief moment of technological capability to probe the stability of the cosmos and pass that knowledge down. This isn't about preparing for an imminent catastrophe. The timescales involved are likely millions of years, but about ensuring the long-term resilience of knowledge itself. If the constants are changing, then our current scientific models are not eternal truths but are instead time-bound approximations, valid for a specific cosmic era. Recognizing this would be one of the most humbling and transformative realizations in human history, forcing a fundamental shift in how we view our own legacy and our place in the deep time of the universe. This challenge inherently demands a new level of global cooperation, transcending national borders and short-term political cycles. Understanding cosmic evolution is a project for all of humanity, requiring the sustained effort of international teams sharing data from telescopes, particle accelerators, and laboratories across the globe. No single nation can shoulder this burden alone. It requires a collective commitment to building the next generation of observatories, funding long-term research programs, and fostering a scientific culture that values patient, meticulous investigation over quick, flashy results. This collaborative spirit is its own ethical achievement, a model for how humanity can come together to address grand challenges that affect us all. It reinforces the idea that the pursuit of knowledge is a unifying human endeavor, one that reminds us we are all passengers on the same pale blue dot, looking out at the same mysterious cosmos and seeking to understand the rules of the game we are all playing. This perspective encourages us to plan not just for the next fiscal quarter or election cycle, but for the next millennium, fostering a proactive and far-sighted approach to science that safeguards our innovations, our society, and our understanding of reality itself for the distant futures we may never see but are undoubtedly responsible for. This conversation about the laws of physics potentially changing over time doesn't just belong to physicists. It sends ripples across the entire pond of human knowledge, touching the shores of biology, philosophy, and even art. For a biologist, the idea of evolving constants isn't an abstract equations game, it's a direct question about the very possibility of life itself. We already know that our universe appears miraculously fine-tuned for life. If the strength of the nuclear forces were a fraction different, stars wouldn't forge the carbon that is the backbone of our biology. Now imagine if those constants weren't just set perfectly once, but are actually drifting. A biologist might ask, is life a single, fleeting accident, a lucky winner in a one-time cosmic lottery? Or could it be part of a much longer, more dynamic process? Perhaps the universe goes through long periods of inhospitable physics, with constants wandering through values that prevent any complex structure from forming, only to occasionally drift into a Goldilocks zone where stars, planets, and biochemistry can briefly flourish. This transforms the story of life from a static, one-time event into a potential cyclical process, where life emerges whenever and wherever the cosmic conditions accidentally align, only to vanish again as the constants continue their slow march. It suggests that biology is not separate from cosmology but is deeply entwined with it, a temporary bloom in a garden whose very climate is set by the deepest laws of physics. Philosophers, for their part, have been grappling with questions of necessity and contingency for millennia. Is our universe the only possible one, governed by laws that could not possibly be otherwise? Or is it simply one contingent reality among a near infinity of possibilities, a random roll of the cosmic dice? The discovery that our laws might be evolving would land like a thunderclap in this ancient debate. It would strongly suggest that the laws are not necessary truths but contingent outcomes. They are the way they are not because of some immutable logical principle, but because of how the universe happened to develop. This pushes the question back a step. If the laws change, what are the meta-laws that govern how they change? Are those meta-laws themselves necessary and unchanging, or could they too be contingent? This line of thinking challenges our most basic concepts of causality and permanence, suggesting that what we call laws might be more like deeply ingrained cosmic habits, patterns that have held for so long they appear eternal to our fleeting existence. It forces philosophy to confront a universe that is not a static being but a dynamic becoming, where even the rules of the game are part of the unfolding story. And what of the artists, the poets, the filmmakers? For them, the notion of a universe with evolving laws is a wellspring of incredible creative potential. It provides a scientific grounding for narratives of cosmic metamorphosis that have always existed in myth and science fiction. An artist might envision a universe where the speed of light was once slower, painting a history where causality itself propagated differently, creating a cosmos of eerie, interconnected synchronicity. A composer could create a symphony representing the slow, deep time drift of the gravitational constant, with themes of structure and collapse woven into the music. This isn't just frivolous speculation, it's a vital feedback loop. Art has the unique ability to take abstract, mathematical concepts and render them into forms that resonate on a human, emotional level. By visualizing and giving voice to these ideas, artists can help the public grasp the profound implications of a dynamic cosmos, making the strange and counterintuitive world of theoretical physics feel visceral and real. They become partners in the exploration, translating data and equations into stories and images that expand our collective imagination. This beautiful, messy collaboration between disciplines is where the deepest insights are often born. A physicist might provide the raw data on quasar spectra, but a philosopher can help frame what it means for our concept of eternal truth. A biologist can outline the precise conditions needed for life, which in turn tells physicists exactly what to look for in their models of varying constants. This interdisciplinary dialogue shatters the old silos of knowledge, revealing that the biggest questions about the nature of reality, life, and consciousness cannot be answered by any one field alone. They require a holistic approach, a meeting of minds where the quantitative rigor of science informs the qualitative depth of the humanities, and vice versa. By talking to each other, we gain a far richer, more nuanced understanding of a cosmos that is not just a collection of particles and forces, but a potentially creative, evolving, and mind-like process, an unfolding story in which we are both the readers and, astonishingly, a part of the narrative itself. Now consider how these mind-bending ideas travel from the rarefied air of academic journals and conferences into our everyday lives. The journey of a scientific concept, especially one as profound as the potential evolution of physical laws, is rarely a straight line. It filters through news articles, documentaries, social media posts, and YouTube videos, each step shaping and sometimes distorting the original nuance. The media landscape thrives on compelling narratives, and the idea that the laws of physics might be wrong is an incredibly powerful headline. This creates a delicate dance for scientists and science communicators alike. The goal is to capture the thrilling possibility and profound implications of the research without veering into sensationalism that promises more than the evidence can deliver, or, conversely, that triggers unnecessary anxiety about a fundamentally unstable reality. This responsibility falls heavily on the shoulders of documentarians, journalists, and content creators. A truly responsible presentation doesn't hide the uncertainty, it makes it the centerpiece of the story. It's the difference between a headline that screams, "Scientists discover physics is broken," and one that thoughtfully explains, "New data challenges the constancy of nature's laws," sparking intense debate. The first creates a false sense of revolutionary conclusion, while the second accurately portrays science as a living, breathing process of questioning and verification. The most engaging science communication shows the sweat and toil behind the discovery, the years spent calibrating instruments, the painstaking analysis of data, the heated arguments at conferences, and the slow, collective march toward consensus. By pulling back the curtain on this rigorous, self-correcting process, we don't diminish the wonder, we enhance it. We show that science is a human endeavor, fallible and messy, but also incredibly powerful because of its built-in mechanisms for finding and correcting its own mistakes. The way we frame this discussion has real-world consequences for public understanding. If the idea of evolving constants is presented as an established fact rather than an active, contentious area of research, it can erode public trust in science itself when the next study inevitably comes out with contradictory findings. Conversely, if it's presented as a fascinating puzzle that the world's best minds are working on together, it invites everyone to share in the excitement of the chase. This approach fosters a more scientifically literate society, one that appreciates the difference between a tentative hypothesis and a well-supported theory, and that understands that a null result finding no change at all is just as valuable a discovery as a confirmed drift. It transforms the audience from passive consumers of facts into active participants in a grand, ongoing investigation, encouraging critical thinking and a deeper appreciation for how we know what we know. Ultimately, the most powerful narratives about our cosmos are those that balance awe with integrity, that inspire wonder without sacrificing accuracy. They allow us to contemplate the staggering possibility that reality itself might be fluid while grounding that possibility in the meticulous, reproducible work of experimentation and observation. This kind of storytelling doesn't just inform, it empowers. It gives people the tools to navigate a complex and often overwhelming information landscape, to ask better questions, and to feel a genuine connection to one of the most profound questions humanity has ever asked. By communicating with care and clarity, we ensure that this incredible frontier of knowledge inspires a sense of shared curiosity and thoughtful reflection about our place in a universe that is far more dynamic and mysterious than we ever dreamed. Deep beneath the earth in the African nation of Gabon lies one of the most extraordinary natural laboratories ever discovered, a place where the universe itself conducted a 2-billion-year-long experiment in nuclear physics. It's called the Oclo Reactor, and it offers us a completely unique way to test the constancy of nature's laws, not by looking out into the distant cosmos, but by looking down into the geological record right here on our own planet. Back in the distant past, conditions were just right for a remarkable event to occur. In a rich seam of uranium ore, natural groundwater seeped in, acting as a perfect moderator to slow down neutrons emitted by the radioactive uranium-235. This slowing down was the key. It allowed those neutrons to be efficiently captured by other uranium-235 atoms, sparking a self-sustaining nuclear chain reaction. a natural fission reactor that hummed along for hundreds of thousands of years before eventually exhausting its fuel and falling silent. This wasn't a human-made machine. It was a purely geological phenomenon, a nuclear reactor built by the Earth itself. For physicists, this ancient reactor is a priceless time capsule. The nuclear fission that occurred 2 billion years ago left behind a specific fingerprint in the form of nuclear waste, products various isotopes of elements like neodymium and ruthenium. The precise amounts of these leftover isotopes are exquisitely sensitive to the physics that govern the fission process, and this is where the fine structure constant comes in. The probability that a neutron will be captured by a nucleus, a value nuclear physicists call the neutron capture cross-section, depends directly on the strength of the electromagnetic force, which is controlled by the fine structure constant. If that constant had a different value 2 billion years ago, it would have altered these probabilities ever so slightly, changing the final blend of isotopes we find preserved in the Oclo rock today. It's as if the universe left us a detailed receipt from a 2 billion year-old transaction, and by analyzing the fine print on that receipt, we can check if the price of fundamental physics was the same back then as it is now. To conduct this audit, scientists have drilled core samples from the long-cooled reactor zones and subjected them to the most precise mass spectrometry analysis possible. They measure the ratios of different isotopes with incredible care, and then they compare those ratios to what our current, unchanging laws of physics predict should have been produced. The results from these painstaking investigations have been, for the most part, remarkably consistent. The isotopic signatures we find at Oclo align very closely with what we would expect if the fine structure constant has remained utterly fixed for the last 2 billion years. This has been a powerful piece of evidence for the constancy camp, a strong counterargument to the tantalizing hints of change seen in distant quasars. It suggests that for at least half the age of the universe, right here in our own cosmic neighborhood, the laws have been rock solid. However, the story isn't entirely closed. Science always lives in the details, and some researchers have pointed out that the models used to interpret the Oclo data have their own uncertainties. The precise temperature and neutron energy spectrum of the ancient reactor are not known with absolute certainty. They are inferred from the geological evidence. Could a slightly different model of the reactor's operation allow for a tiny amount of drift in the constants while still matching the observed isotopes? It's a possibility that keeps the investigation alive. Furthermore, as our analytical technology improves, allowing us to measure isotopic ratios with even greater precision, we might be able to detect variations so minuscule that they were simply invisible to previous generations of instruments. The Oclo reactor, therefore, isn't a single, definitive answer, but an ongoing experiment. It demonstrates the incredible power of using our own planet as a scientific instrument, providing a crucial data point from a specific time in cosmic history that complements but also challenges the data we gather from the far reaches of space. It reminds us that the search for cosmic truth isn't confined to giant telescopes. Sometimes the most profound clues are buried right beneath our feet, waiting for us to dig them up and read their ancient story. Any great scientific revolution begins not with a sudden explosion of consensus, but with a slow burn of intense, rigorous debate. And on the question of whether the universe's deepest laws are changing, that debate is currently in full swing, dividing the physics community into passionate camps of skeptics and proponents. This isn't a conflict to be resolved quickly. It is the essential, healthy engine of scientific progress, where every claim is met with a demand for stronger proof and every counter-argument inspires more ingenious experiments. On one side, you have researchers like John Webb and his team, whose analysis of quasar light first threw down the gauntlet, suggesting the fine structure constant alpha was slightly smaller in the distant past. For them, the evidence isn't just a collection of anomalous data points. It's a tantalizing whisper from the cosmos, a pattern consistent enough across the sky to hint at a profound new truth. They argue that to ignore this pattern is to risk a failure of imagination, to be like those who dismissed continental drift because they couldn't conceive of moving land masses. Arrayed against them are the skeptics who play the equally vital role of the community's immune system. Their position isn't one of closed-mindedness but of profound respect for the known. They argue that extraordinary claims require extraordinary evidence, and that the potential for hidden systematic errors in these ultra-precise measurements is immense. Could the observed spectral shifts be caused by unknown chemical contaminants in the ancient gas clouds? Perhaps different isotopes of elements were more prevalent billions of years ago, subtly altering the absorption lines without any change to the fundamental constants. Maybe the issue lies not in the cosmos, but in our own instruments, a tiny, unaccounted for temperature fluctuation in a spectrograph on a mountaintop in Chile that could mimic a cosmic signal. Their mantra is to first exhaust every possible mundane explanation within the standard model before invoking a paradigm shift that would rewrite the textbooks. Key figures in this camp have meticulously reanalyzed the same quasar data, applying different statistical models and calibration techniques, and in some cases, they have found no significant evidence for variation at all. This back and forth is not a weakness of the scientific method, it is its greatest strength. This intellectual tension plays out not in isolation but in the vibrant, collaborative, and sometimes heated forums of international science. Major conferences on cosmology and fundamental physics often feature dedicated sessions on varying constants, where proponents and skeptics present their latest findings side by side. These are not hostile confrontations but deeply engaged discussions where a theorist might stand up and challenge an observer's error margins, or an experimentalist might question the assumptions in a skeptic's reanalysis. Papers are published often in response to other papers, each one refining the arguments and tightening the constraints. Through this process, the goal isn't for one side to win, but for the entire community to collectively converge on the truth, whatever it may be. The scrutiny faced by researchers like Webb is intense and personal, but it is also a form of respect. It means their work is considered important enough to warrant such fierce examination. This self-correcting mechanism, while slow and often frustrating, is what ensures that if a discovery is finally confirmed, it will be on a foundation of evidence so solid that it can withstand any doubt. It is the sound of the scientific community doing its job, carefully weighing whether the universe's laws are indeed written in immutable stone, or in a subtler ink that might, just might, be capable of fading over the deep expanse of cosmic time. So if these isolated clues from quasars, atomic clocks, and ancient reactors are indeed pointing toward a deeper truth, we must step back and ask the most important question of all: what would it mean for our overarching story of the cosmos? Cosmology is at its heart the attempt to write a single, unified history of the universe from its first moment to its last. For decades, our standard model of cosmology has been incredibly successful, built on a foundation of fixed, immutable laws. It's a magnificent edifice, but one that has recently begun to show cracks. Puzzles like the Hubble Tension and the mysterious nature of dark energy that stubbornly refuse to be solved within the existing framework. The introduction of evolving constants isn't just about patching these cracks, it's about envisioning an entirely new kind of foundation, one that is dynamic and alive with change. This transforms our entire cosmic narrative from a static description into a sweeping historical epic, where the laws of physics themselves are characters with their own story arcs. Consider one of the most fundamental observations in all of cosmology, the stunning flatness of the universe. Our measurements tell us that the geometry of the cosmos is almost perfectly flat, a very specific and seemingly improbable outcome that required the expansion rate and the energy density in the first moments after the Big Bang to be balanced with unimaginable precision. To explain this, physicists proposed the theory of inflation, a brief period of hyper-accelerated expansion that ironed out any curvature. But inflation itself requires very specific conditions to begin and end. What if the parameters needed for inflation weren't just a lucky initial condition, but were themselves the result of evolving constants? A universe where the strength of gravity or the nature of scalar fields was different in that first fraction of a second could naturally and inevitably trigger an inflationary phase, making a flat universe not a mysterious fine-tuning but a predictable outcome of a deeper dynamic physics. This would elegantly solve the problem, weaving the flatness of the cosmos directly into the evolving biography of the laws themselves. This dynamic perspective could also provide the key to unlocking one of the greatest unsolved mysteries: why our universe is made almost entirely of matter, with virtually no primordial antimatter left over. According to our current models, the Big Bang should have created equal amounts of matter and antimatter, which would have promptly annihilated each other, leaving behind a boring sea of radiation and nothing else. The fact that we exist is proof that something must have tipped the scales, a process known as baryogenesis. The standard mechanisms proposed for this rely on conditions and particle interactions that, so far, we have been unable to confirm. But if the constants governing those particle interactions were not constant, if the behavior of the fundamental forces was slightly different in the extreme heat of the very early universe, it could have provided the perfect environment to favor the creation of matter over antimatter. A tiny, early drift in the strength of the nuclear forces could have been the cosmic bias that made all the difference, explaining our existence not as a random accident, but as a consequence of the universe's evolving rulebook. Even the dark sectors of the cosmos, dark matter and dark energy, could be profoundly intertwined with this idea. Dark matter, the invisible scaffolding that holds galaxies together, is currently thought to be a stable, unchanging substance. But what if its properties or its interaction with normal matter have evolved over time? This could explain puzzling observations in the population of dwarf galaxies or the distribution of matter on the largest scales. And dark energy, as we've discussed, might be the most dramatic example of a dynamic constant itself. Its perceived behavior could be the most visible sign of a deeper evolution happening across all the forces of nature. By allowing the constants to vary, we aren't just adding new variables to our equations, we are inviting a new principle of cosmic evolution into the heart of our models. This could lead us toward a new standard model of physics, one where the apparent laws we measure today are seen as the current equilibrium state of a much richer and more complex system, a system that has been changing and developing for nearly 14 billion years. This wouldn't destroy our current understanding. It would complete it, placing our successful, static models within a grander narrative of transformation, revealing a cosmos that is not just expanding but truly growing up. This idea that the very bedrock of reality might not be permanent is perhaps the most humbling and awe-inspiring thought we can entertain. It strikes at the very core of what we mean by reality itself. We are accustomed to thinking of the universe as a grand, majestic machine, operating according to a set of instructions that were fixed at the moment of creation and will remain unchanged until the very end. This view offers a certain comfort, a sense of order and predictability. But what if that's not the whole story? What if the universe is less like a meticulously crafted clock and more like a living, breathing entity, one that is capable of growth, adaptation, and even self-revision over the almost incomprehensible spans of deep time? This shifts our perspective from a cosmos of being to a cosmos of becoming, where change is not just something that happens within the universe, but something that happens to the universe's very rulebook. This profound shift forces us to reconsider the nature of knowledge itself. For centuries, the goal of science has been to uncover the eternal, objective truths of the cosmos. We have sought the final equations, the ultimate theory of everything that would explain all phenomena for all time. But if the constants are drifting, then our most brilliant theories are not timeless revelations. They are more like incredibly detailed snapshots of a specific cosmic era. They are not wrong, but they are provisional, accurate, and powerful descriptions of how things work now and for the foreseeable future, but potentially incomplete in the grand, billion-year narrative of the cosmos. This doesn't devalue science, it historicizes it. It transforms our quest from a search for static, final answers into a participation in an ongoing, unfolding story of discovery. The Holy Grail might no longer be a single set of immutable equations, but rather the discovery of the meta-laws, the deeper principles that govern how and why the apparent laws themselves evolve. On a deeply personal level, this cosmic perspective can reframe how we view stability and change in our own lives. We often crave permanence and fear uncertainty, seeing change as a disruptive force. But the universe itself, in this grandest possible view, suggests that change is not an anomaly. It is the fundamental engine of existence. The constants that allow for galaxies, stars, planets, and life may have themselves emerged from a long process of cosmic evolution. This invites a beautiful metaphor. Just as the universe has gradually complexified over billions of years, moving from a featureless soup of particles to the structured, awe-inspiring cosmos we see today, our own personal growth often follows a similar path. Our understanding, our character, and our lives are not fixed at birth. They are dynamic projects continually evolving through experience and learning. The chaos and uncertainty we sometimes feel can be seen not as a failure to achieve stability, but as the necessary raw material for our own becoming, our own personal version of cosmic evolution. It connects the very large to the very small, suggesting that the same creative impulse that shapes galaxies also operates within us, driving us to learn, adapt, and grow. This isn't just physics, it's a philosophy for embracing the dynamic, unpredictable, and wondrous journey of existence itself. We began this journey anchored by the assumption that the universe operates under a single, unchanging set of rules, a belief so deeply ingrained it feels like common sense. But as we've traveled from the philosophical certainties of the ancient Greeks to the quantum uncertainties of the modern era, that foundation has been beautifully, thrillingly shaken. We've stood with astronomers analyzing the ancient light of quasars, hunched over the impossibly precise ticks of atomic clocks, and even dug into the geological remains of a 2-billion-year-old natural nuclear reactor. At every turn, the question has persisted, not as a fringe idea, but as a serious scientific inquiry. Are the laws of physics themselves written in permanent ink, or are they more like a draft that the universe is still subtly editing? The evidence, as it stands, is a masterpiece of scientific tension. There are tantalizing shifts in the spectral lines of distant atoms, puzzling discrepancies in the universe's expansion rate, and theoretical frameworks like string theory that not only allow for change but demand it. Yet for every hint, there is a healthy, rigorous skepticism. The Oclo reactor suggests remarkable stability, while the incredible precision of our measurements means we must constantly guard against our own instruments fooling us. This is not a sign of a broken process. It is science at its absolute best. It is the sound of countless brilliant minds working in concert, challenging each other and slowly, painstakingly inching toward a deeper truth wherever it may lead. And that perhaps is the most important takeaway. The answer to the question itself, yes or no, is ultimately secondary to the magnificent endeavor of asking it. This pursuit pushes our technology to its absolute limits, inspires new generations of thinkers, and forces us to confront the most profound philosophical questions about the nature of reality, knowledge, and our place within it all. It reminds us that the universe is under no obligation to be easily understood by human minds. Its mysteries are deep and layered, and our role is not to assume we have all the answers, but to remain perpetually curious, forever willing to be humbled and astonished by what we might find. So the next time you look up at the night sky, remember that you are not just looking at a collection of distant stars. You are gazing into a living, breathing cosmic story that may still be writing its own rules. The conversation is far from over, and your perspective is a part of it. Let us know what you think in the comments below. Do you believe the cosmos plays by a fixed set of rules, or is reality a more fluid and dynamic masterpiece? If you enjoyed this deep dive into the mind of the universe, be sure to subscribe and hit the notification bell so you don't miss our next journey into the unknown. Until then, keep watching.